Okay, so now let's get back to both the primal and the dual version, and let's see what happens when you solve the primal or the dual version. How do you classify? What's your final classifier? Okay. In the primal version, the final classifier is very easy. So the final classifier, G of X is just equal to the sign of W star transpose X plus B star. Okay, so you solve this problem, you get W star B star, it's the sign. Okay. You can do the same thing here. You can solve this problem, you can get W star B star, and you can plug it into that final hypothesis, exactly the same. Okay. But now we're going to address the issue of trying to get rid of all dependence on dimension, all dependence on the actual feature vectors. Okay. And with a view towards the fact that these feature vectors, xn, xm, for example, and xn here, when we transform to a nonlinear feature space, those become z's. Okay? And if that nonlinear feature space is very huge dimensional, then these are unwieldy vectors, and we'd like to get rid of dependence on them. Okay? And so the first thing we will observe is that, well, we have a functional form for W star. So let's look at what this function looks like. Okay, so when we plug it in, so now we can get rid of this. So when we plug this in, we get that our final hypothesis G of X is equal to, it's the same, it's the sign of W star X, W star transpose X plus B, but now we know what W star is and we know what B is. So it's the sign of this guy transpose. So the sum from n equals 1 to big N, okay, alpha n star, okay, yn, xn, and we take the transpose, so transpose times x, put this in parentheses, okay, plus b star. Okay. But what is b star? So plus, okay, plus a b star. Okay. But what is b star? So b star, it's just a number, so that doesn't depend on dimension, it's just a single number. It's b star is equal to ys minus, okay, so W star, but we know what W star is, minus the sum over your data points, alpha n star, or yn, xn transpose, so W transpose xs, where xs is a support vector. So you can compute this B star, okay, and now you see that I've entirely represented the final hypothesis using just my support my Lagrange multipliers at the optimal, my target values, and my data points. Okay? So this entirely depends on alpha n star, yn, and x, the x values, so xn and x, okay, so xn and x. Okay. But it doesn't depend in an arbitrary way on my xn and x's. Okay. So let's look at the computation of B star. The computation of B star only involves the dot product xn dot product xs. Okay, so it only depends on xn dot product xs, okay, and xn dot product x, xn dot product x. Okay. So my final hypothesis only depends on dot products. Okay. You might have observed a small issue with this final hypothesis. If I represent the final hypothesis in this way without actually computing W star and B star, okay, then in order to deploy my final hypothesis, I need to have all my data points. And it seems like I'm ending up in the same situation as I was when we talked about the nearest neighbor algorithm. When you want to deploy, you have to use all your data. Well, it turns out, and as you saw in that example, that very often, many of these alpha n's are 0. So you only really need to keep the data points which are support vectors. Actually, you can compute the B star, as one number, okay? But in order to deploy your final hypothesis, you only need the terms in this summation which are non-zero, which correspond to support vectors, the alpha n's which are non-zero. And that's a huge savings, a huge improvement over, for example, the nearest neighbor computational demand of having to carry around all the data with you. Okay? So that's a huge savings. Even though it looks like we have to carry around all the data, we don't. Just pointing that out because many of you might have observed, wow, so we have to carry around all our data to classify? No, only the support vectors. And usually there are very few support vectors. Okay? Now, so let's get back to this main observation that the dependence on this final hypothesis on the data is only through dot products. And then I'll make one more observation. If we look at how we got the optimal alphas, we solved an optimization problem. What does this optimization problem depend on? Well, you've got your optimization variable alpha, and then the parameters that you have to send in are the target values yn and the data xn and xn. But you don't need to send in the data. You only need to send in this matrix GNN. Okay. So to get the alpha n star, we only need the matrix G, i.e. GNM, which is xn transpose xm, or xn dotted into xm. This is what we need in order to get the alpha n star. And you will observe that again, all I need are dot products. Or specifically this matrix G. This matrix G is sometimes called the Gram matrix, the matrix of dot products. Okay. Well, technically we define the matrix as the signed Gram matrix that also involves the y's. But if you give me the matrix of dot products, which is what conventionally is called the Gram matrix, I have enough, all the information I need because I also have the y value. So this is an n by n matrix. So this is an n by n matrix. This is, the target value is n by 1, matrix of dot products. Okay, the target vector is n by 1 vector of target values. And these together allow me to get alpha n star. Alpha n star gives me, the ability to compute the final hypothesis G. And in order to compute the final hypothesis G, well, I've computed B star using just dot products. Okay, so these terms are already in this Gram matrix. And I need the ability to compute the dot product between my test X and my data points, my support vectors. Okay. So the entire algorithm depends only on the ability to compute dot products. And such algorithms are called inner product algorithms. Well, the dot product is called an inner product. So such algorithms are called inner product algorithms. Okay, these are very convenient algorithms. Because in order for this entire algorithm to run, so in order for us to be able to run the entire optimal maximum margin hyperplane algorithm, in order to run this entire algorithm, all we need is the ability to compute dot products. You don't even need to give me the data. If you give me a function that can take as inputs, data points and spits out the dot product, that's all I need to run this optimal hyperplane algorithm. So let me show you how. So supposing you gave me a function. Give me a function. And I'm going to call this function k. And it takes as two arguments, one vector and another vector, okay, k, of two arguments. Let's call it x and x prime. And it returns x dot x prime. Okay. We call this a kernel. Okay. Then I can run the entire optimal hyperplane algorithm. Here's how. The optimization problem, minimize over alpha. 1/2 the sum over n and m, alpha n, alpha m, yn, ym, my kernel on xn and xm, minus the sum over n, alpha n. So that's the objective. Subject to sum over n, alpha n yn equals 0, and alpha n is greater or equal to 0. This gives me alpha n star. Once I have alpha n star, my final hypothesis g of x is equal to the sine of sum over n, big N, alpha n star, yn, my kernel of xn and x, okay, plus b star, where b star is just equal to ys, okay, minus the sum from n equals 1 to big N of alpha n, yn, my kernel of xn and xs, where xs is a support vector. A support vector, which means alpha s is bigger than 0. Boom! I've represented this entire algorithm and the final hypothesis using what? Using just the ability to compute dot products. Okay. And this dot product, okay, is just the dot product in whatever space you're in. Okay, so now let's look at what happens. So let me erase this. So such algorithms are called inner product algorithms. By the way, everything I'm about to discuss now applies to any inner product algorithm, an algorithm that only needs the ability to compute dot products. And it turns out, and that's another beauty of the optimal hyperplane algorithm, it's an algorithm that only needs inner products, that only needs dot products. Inner product algorithm. Okay. So now let's see. So now let's see what happens when I transform into a feature space.